Okay, so here I was explaining that we were defining that ZY axis or ZY plane. So now this plane is passing to the oxygen. Oxygen half portion would be reflected by the other portion, right? So when we have a plane, this hydrogen is getting reflected by this hydrogen. So this plane is also passing through your Z axis. So sigma ZY is also being called as a vertical plane, right? So both the planes that are existing in water that are vertical planes which are passing through your C2Z axis, which is the axis of symmetry. Okay. So if you guys have any question, you can unmute yourself. Other than that, please keep yourself muted so that there won't be any disturbance. Thank you. Okay, I was coming to this point. Now, if I need to find out whether there is a horizontal plane or not, how do we define it? The only plane which can be called as a horizontal is left as sigma xy, which is perpendicular to your z-axis, because this plane, if you will see, if I'll highlight with purple, this is the plane. And if this is the plane and it is perpendicular to your z-axis, the pen that I'm showing, that is z-axis, and down one is your xy plane. Now, if I was having a molecule on zx plane, that oxygen, water, H and H, even if I'll try to put in this particular form and water molecule is there is nothing which is getting reflected down. So therefore, this sigma xy is not giving me any equivalent orientation. So sigma xy is not present. Therefore, no molecular or horizontal plane is present in your water molecule. So only symmetry elements are present. That is your C2 along the z-axis. The one angle is zx, and the other plane is the one plane is zx, and the other plane is your zy. Is it clear?
Yes, ma'am.
Okay. So this is how we define it as a plane of symmetry. The third, we will quickly take it up, like whatever the 3-4 examples of the symmetry elements are left, then we'll start up with the assignment questions. The third one that we have is your improper axis of symmetry. So improper axis of symmetry, we define it as by the symbol as SN. The proper one, we have.
Call bucket. Hey, harap bucket.
Okay. So the proper axis of symmetry was denoted by Cn. Now here improper is being denoted by Sn. This is actually a combination of Cn and your molecular plane. For example, if I have S2, if I have to define the improper axis of symmetry S2, that would be a combination of C2 along one particular axis. If I've taken Z as the main axis, so the plane has to be perpendicular to that Z axis. That would be your XY plane. So this way, how we define as improper axis of symmetry. And even if the molecule is not having C2 or sigma independently, or Cn or sigma independently, there is a high possibility of having your Sn existing over there, that we will see corresponding with respect to the example. The fourth one is your inversion center. So the inversion center is being defined as I. So something which is there, and for example, if I have this molecule, this is peroxide, hydrogen peroxide, H2O2. So this is my center. And if from the center I'm going to the opposite sides and I'm getting the similar molecule, that is where we call it as it is having an inversion center. That means at 180 degrees or at equal opposite ends, we are getting the similar kind of atom. That is where we call it as symmetry is existing, which is inversion center. For example, if I go equal distance from here to this side, I'm getting oxygen on oxygen. It is fine. And here, if I'll go from here to this side, I'm getting hydrogen. Similar distance I am covering and I'm getting second hydrogen. That is also right. So all the atoms of that particular object has to be having an inversion center. We can't call it as, okay, two are matching, other twos are non-matching. So that can't be an inversion center. For example, if I'm taking this case, I have taken benzene. Here, everything is H, 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 and H. So can you please tell me whether inversion center is existing in this molecule or not? You have to go from the center to opposite ends to every atom and see whether same atom is existing or not. So is it there or not?
Yes, sir.
Yes. So
Yes, it
inversion
is.
center is there. How? If I'll consider this as a center, if I'll take it as a resonance structure, this is my center. And here I'm going one side on this hydrogen, other side on this hydrogen, equal, that is existing. Here also it is existing on the opposite side, and here also it is existing on the opposite side. Whereas if I have taken a next molecule, where I will replace one hydrogen with the X. Now this is hydrogen, this one. All are hydrogen except this one. This is X. Now you tell me, if I'll go from this center to this center, hydrogen and hydrogen are matching. With respect to these hydrogen, inversion center is there. With respect to these hydrogens also, inversion centers are there, which are almost at 180 degrees of each other. But what about this one? With X and this one, is there any inversion center?
No.
Right. So even if the four atoms are actually on opposite sides of each other, we can't claim it as an inversion center until and unless all the atoms of the particular molecule are acting in the same way. So if this is X and it is not matching, it is not having an inversion or opposite side, that means it is not having I. So inversion center is not there. And the last element that we have to consider is
One more doubt I have.
yeah.
So in the last case, even in the other hydrogen also, if you replace by X, that time you can call it as inversion?
Yeah, we can call it as an inversion center because it would be having all the atoms at the, you have to go on the 180-degree angle, and on the opposite side, you need to have a similar atom. So if I'll replace this by this particular X and this is X, that is also what we call as a inversion. Yeah, that would be happening.
Thank
you. So the next question, the last element we have is identity operator. That we have already discussed, but still we are talking about. So identity operator is something when we are giving a rotation of 360 degrees and we are getting exactly the same structure. For example, it is not even called as the equivalent. That is where I was focusing on this equivalent and identical. There are two differences. So equivalent is something when I am having water and this is 1 and this is 2. After some rotation, it is becoming H2 and this is becoming H1. That is called equivalent. That is not identical. But if something happens and I am giving it 180-degree rotation, so it would be coming as H2, H1. Another 180-degree rotation, it will give me H1 and H2. So this H1 and H2 and this H1 and H2 are similar. They're properly identical. So that is where we call it as E. This is the identity operator where E is your symmetry element that is existing and which is giving you an identical symmetry. Here in this one rotation of this 180 degree, it is giving an equivalent symmetry. And when you are giving 2 times 180 degree, that becomes as 360 degrees. Similarly, if I will repeat 120 degrees 3 times, 120 at one time, another 120, then 120, that will give me an identical identical symmetry. That is where the identity operator comes into picture. So this was all about the symmetry elements and operations. I hope you have understood well. So we have covered so far the symmetry and the chirality. We have covered symmetry and energy relationship. And we have also covered the symmetry in mathematics, which is defining operators and elements. I hope you have understood well. If there is any question, before I would start the assignment question, I would like you to unmute yourself or put it in the chat box.
And then every system will have identity, isn't it so?
Yeah, every system would be having identity. So identity becomes the it is there. Any element is there or not, but identity operator would be there. Element would be there in every single system.
Okay, ma'am.
Okay, so now we will start the questions. So the first assignment question that we are taking up, so since we have discussed a lot about the proper axis of rotation and improper axis of rotation, so the first question says, find out the total number of proper axis of rotation and improper axis of rotation operations present with the BF3 molecule. So we have, I would like you to try on your own and then I will explain. If you can get this answer, that would be really good. Anyway, we are going to explain and have a discussion about it. So I will just make this molecule. This is also one question. How do we get to know that BF3 is going to be in a trigonal planar? So there you need to understand the valence shell electron pair theory. And if I am having a boron, which is having an atomic number of 5, it would become 1s2, 2s2, 2p1. And if I have to have its hybridization, there it would be one electron can go and get excited over there. And this would become. So whatever the valence electrons and empty ones are there, that would make your sp2 hybridization. I hope this is clear for everybody. If there is any doubt, you can go back and read the valence shell electron pair theory and all over the chemical bonding basic concepts, because that would be a lot to cover in this particular lecture. So this is how we get to know that sp2 is going to give you a trigonal planar, because there is no unpaired electron or there is no pair of electrons are there. So only it can form is 3 bonds. So fluorine, the other fluorine and the third fluorine. And this fluorine, we can define it as boron, one fluorine, F2, the other one, and F3. Now we need to find out what axis, that CN axis is there, and how many operations are there. That is very important to understand.
C3 is there.
Sorry?
C3 axis.
C3 axis is there. Okay, fine. But how many C3 you can apply? That number I need.
Only one.
No. How? Okay, you said only one. If I'll apply 2
One
times
C3,
C3,
then you won't get equivalent one. No? You will get equivalent one, not the identical one.
right? But equivalent is fine, no? After 1 C3 also we are getting equivalent. So why not the 2 times?
I mean, you get C3 axis in the sense if you rotate 3 times, you get your identity. That's
right,
my.
right. So what about when I rotate it by 2 times?
Then
You're coming at the right point. I will just explain it, but I want to hear it from you. You're absolutely right. When we do it 3 times C3, that would give you an identity operator. But I'm saying when I'm doing it 2 times, why not then 2 times we can have an equivalent orientation? 2 times is also fine, na? Because for 1 time C3, we are getting equivalent. 2 times also we are getting equivalent. 3 times only we are getting identity.
yes, ma'am. Yeah, correct.
So for C3, that means there are 2 operations that can be applied. Okay, that is clear. So this is where we have to understand that when I'm talking about the proper axis of symmetry operation, then you just need to see what are the C is there or not. Say, for example, we have taken this C3. So we know that C3 is existing in this BF3 molecule because after giving a 120-degree rotation, it is giving an equivalent orientation. There is one more axis of rotation existing in this BF3. C3 becomes the highest, right? C3 is the highest.
Yes.
And number of 3 is highest. Is there any lowest one?
C2 is there. Along one BF, the other 2 will become reflection.
Yeah.
Like other 2 will.
There are 3 C2s also along each BF bond, right?
Yes, ma'am.
So now see. Now C3 I have applied for 1 and I need to define that C3 is going through my boron atom. So after giving the C3, that is a 120-degree rotation, what will come on at the place of F1?
120 in the clockwise, ma'am, or
Anything is okay. Go by clockwise.
F3 should come.
Yeah. So F3 will come here. This will come as F1 and this will be F2. That is 1. Now if you'll see the image 1, A and B, are they identical?
They are not identical but equivalent.
Equivalent. So that is okay, right? Now if I'll give C3 2, that is a another rotation. C3-2 means one C3 is gone, another C2-3 I'm giving. So I should not write it actually as C3-2. So this is another C3 I'm giving, right? So one more C3,
Okay.
120 degrees rotation. Now what would be above? That would be F2,
F2, F3 and F.
F1. Is this equivalent or identical?
They are equivalent.
Yeah, this is again equivalent. So this is also valid. Until and unless we are getting
Yes.
equivalent or identical, that is fine, right? Now give one more C3. What would be the places of the F fluorine atoms?
1, 2, 3.
Yeah, so this is F1, this is F2, F3. Now see the image D and A.
Yes, V and E are identical now.
They are identical. So from there we got to know that when we applied C3 one time, that is fine. It is giving us equivalent orientation. C3-2 is also fine. That's a 120. That's a 240. But C3-3 is equals to E. So if I talk about how many total proper axes of operations or the elements are there, that would be only 2. We do not consider C3-3 because it is no more a proper axis of rotation. It becomes an identity operator. So that number
Okay, so
becomes
identity is not considered in the proper axis.
right. Identity is a different symmetry element. It does not come under the proper axis. We are talking about the how much Cn is there. Even if it comes under C3-3, that is equivalent to identity, which is already been counted. So now total proper axis of operations would be 2, right? So C3 will give you 2. What about C2? If I have BF1, 2, and 3, and I'm going along BF1 bond, this bond. So along this, I am having a C2 axis. So now what would be the configuration?
2, 3 will be left and right respectively.
Yeah, so that would be having F, this is again equivalent, right?
Yes.
So if I do one more C2 to this, what will happen? Along the
Then
same
you get identical. You get identical.
So we get the identity, that E operator. That means now if I'll talk about the total proper axis of operations along the C2 axis, how many you will get?
1.
Right. So C2 you will get only 1. So this gives you a generalized statement. Whenever you have Cn proper axis of symmetry, it will give you n-1 operations.
Okay.
So when we are talking about order is something you need to include all the number of elements or operation. You need to consider all of them. So there you cannot just say that C3 is there and other won't be there. If C3 is there, you need to consider that how many operations it is going and including into it. Okay. So Cn would give you the n-1. So for example, C3 is going to give you 2 operations. C2 is going to give you 1 operation. If I'll talk about C4, automatically it becomes 3 and so on and so forth. So this is how we calculate. So in case of the BF3 molecule, if we talk about C3, with respect to the C3, there are 2 proper axes of rotation. With respect to C2, there are 1. So total number becomes 3. Is it clear?
Okay. Yes.
Now the question that I asked, it was that, okay, now total number of proper axes we calculated. What about the improper axis of rotation operations? Similarly, we have to calculate the improper, we have defined it as
Cn plus 1 plane, I think.
Cn.
One S axis is some the earlier rotation plus 1 plane reflection.
That is multiplication. We can't call it as a plus. So this is actually written as Cn into sigma. Like if you apply the reflection first and then rotation, or rotation then reflection, so it has to come as a multiplication of the 2 symmetry elements, right? So we know that, okay, we have a C3 axis. So corresponding to that, we can consider S3 would be existing. We don't know whether it exists or not. We need to check first. Okay. So we have BF1, F2, F3. So what is C3? S3, it would be C3 along, say for example, Z axis and sigma along XY. Is this definition clear?
Yes, ma'am.
There is only one C3. So now we will see whether it is existing or not. So first we will apply whatever the operation is on the right side, that would be applied first. So this is C3 and the right side is sigma. The plane has to be applied first. This is according to the rule of this multiplication. So we are applying sigma xy. So when we are applying sigma xy, we need to consider that this is a molecular plane. This is already existing in a molecule. So BF3 molecule is a trigonal planar. It names itself suggests that it is in a plane, right? So the z-axis was going through the boron, and boron, fluorine, and every fluorine is on the plane. So it is going like this way. Now I'm talking about xy, which is perpendicular to my z-axis. So it will cut all the boron, fluorine, and fluorine into equal halves. Like half of the boron would be above, half of the down. In between, there is a plane. So this is not going to change anything. This will give you F3, F3 or F2. It is just upper half is going like down half. Is that clear?
Yes, ma'am.
Okay. Just a second. So now one operation we have done. Now what about the C3Z? It has to go through your boron. It is going through your central atom. So we have already applied the C3 before. So it will come as F3 would go above. This is F1, this is F2. Now, if you start with this A image and you ended up having this image B, are they equivalent?
They are equal.
Yeah, so they are equivalent. So that means S3 is existing. That is for sure. Firstly, to know the number of axis operations, we need to know whether that is existing or not. Somewhere S3 will not be exist because of that multiplication that will not give you an equivalent symmetry. So S3 is existing. Now the question is we need to find out how many operations of that S3 is existing. So we will do it in mathematical way. S3 has to, we have to see all the possibilities of S3 until unless identity will come. So S31 would give you C31 into sigma 1. This is in horizontal, that is self-understood. So C31 and sigma h, we know that it is an improper axis. So there is no particular name or it is not converting to any other element. So this is existing. Now what about S32? The 2 will come as C32 and sigma h2. So C32, like 120 and after 120 degrees. That would be C32 itself. What is the square of the sigma? If I have applied, this is one hand, this is another hand. I have applied plane over here.
It will come same.
What will come soon?
No, sigma, if you apply second time. then
It will
is
come as an identity.
same.
It will come as an
Yes.
identity, right? So
Identity, yes.
C32 into identity will give you C32. So now if you see, your improper axis has turned to proper axis. Agreed? So this can't be counted as your improper axis of operation. While counting, we cannot count the C32 as your improper axis of rotation. Now, if we'll go to S33 three times. Now, what would be your answer? First, C, you have applied C3 three times. What would be that?
You get identity in the rotation and you get sigma h.
Yeah.
1.
So that would become as a sigma h. Now your
Yes.
improper axis has converted to your molecular plane. That also can't be counted. Now go beyond. Until unless we get total product value as E, we won't stop. So S3, 4 times, C3 into 4, sigma H into 4. Now C3, 4, that would come as
C31.
right. So
Similar to
ultimately,
C31.
yeah, so it is C31, sigma H, so it will become as C31. So again, your S34 has turned to C31. Now the fifth one is, if I'll do it 5 times, this would come as C32, this would come as your sigma H. Odd and odd, so it would come as like this way. This would be counted. And the last one would be S36, C36, sigma H 6. C36 is nothing but 2 times 360 we are doing. So it would become
Yes.
identity into identity. That would be identity.
Yeah.
Now we have reached identity. That means the operations have stopped.
Clocked.
More
Okay.
than identity, we don't have to go anywhere. So we started with S31. We ended up having S36. But out of these 6 operations, out of S31, S32, 3, 4, 5, and 6. This is counted because this is C31 sig match. So it is not giving us any other value. S3 can't be counted because it was giving us C32. S33 can't be counted because it was giving us sig match. S34 was giving us C31. S35 would be counted, and this was giving us identity. So out of all the 6 operations, which one would be counted as your improper axis of operations?
I think fifth one.
Right, fifth one is there, and
First one.
right. So only these two, because rest of the things have been converted to other symmetry operations, either C3 or sigma or identity. They are no longer the improper axis of rotation. And once they, why are we not considering them? Because firstly, they are not improper axis, and secondly, they will already be counted as their own. Like C32 we have already counted, sigma we have already counted, and identity also we have already counted. So 2 times repetition we can't do. So this S3 operation, that symmetry element, is going to give you 2 operation, S31 and S35. So it would be counted as 2. So the answer of your question was this one. The proper axis of rotation for BF3 molecule, if we are considering C3 also as well as C2, it was giving us how many? 2 were coming from C3 and 1 was coming from C2, but there were 3 C2s we are counting as a 5, and improper axis of rotation operations we are coming as 2. Is that clear?
Yes, ma'am.
Okay, so now we are moving to the second question. Second question is predict the equivalent structure on applying following operations on PTCl4. So PTCl4 platinum chloride, it is having a square planar geometry.
Square planar.
Okay, so it is like this way. So if I'll define it 1, 2, 3, and 4. Now you have been given the operations and you have to apply it on your molecule. So first, if you will see, after giving C4 is what? How much angle of rotation you have to give?
C4 is 360 by 4 is 90 degree.
Okay. See, so rotation we are giving as 90 degrees, right? So but this C4 has to pass through what?
I think it has to pass through.
Yeah. So when
it has to pass through platinum.
C4, all the 4, there should be at least 4 atoms which are moving. Then only we are defining it as a 4, right? So that C4 is going to pass through your platinum. That Z-axis is along your platinum, and you can consider a square where all the Cl are at the 4 edges and at 4 vertices, and your platinum is in the center, and your axis is like this way. Now I'm rotating like clockwise direction, 90 degree. This Cl1 would go to Cl2 position, and we will get
3 will become 4.
This will become Cl.
1 will become 2, 2 will become 3, 3 will become 4, 4 will become 1.
So this is after your C4 operation, right? Should I draw it in another slide? We will draw it properly.
No, it's fine.
Because actually I have to show that sigma H is also there. So anyway, we can draw that again. Cl1, 2, Cl3, Cl4.
And can we predict the symmetry from the hybridization itself?
Not really, but yeah, we can do one thing that would be covered in the week 2. For example, you don't have to memorize all the time, or you have to define all the symmetry elements for each and every molecule. For example, if something is coming as a shape of water, you understand that water is having certain shape, and similar to that, if you're having another shape, that would be having same point group, similar kind of elements, because just the atoms have been replaced and you're having the similar kind of thing.
So just you have to correlate with the known molecules.
So that is where the point groups and the symmetry become very important. You don't have to mug up, or you do not have to find out each and every time. So for the basic systems, if you have defined it, you can easily consider it and correlate with other structures also. For example, here I have taken platinum Cl, right? The 4 Cl. Any Ml4 complex, any
square planar will have similar symmetry.
Similar kind of symmetry. You do not have to draw it again. You do not have to find it anything. It would be following the same thing. I don't know why it is again ending. Sorry for the inconvenience, but the meeting again will end in 10 minutes. So you have to rejoin. Okay?
Okay, ma'am.
Zoom is giving me only like 40 minutes of time span. I will figure this out later, but yeah, you again join it. So here we were. So we applied C4 along the Z-axis, that is along your platinum, and this is becoming Cl4, Cl1, Cl2, and Cl3. So this was first operation, and first operation we have applied. We got an equivalent orientation, and that means C4 is existing, that we have proved. Now, second, we have to apply sigma H on this molecule. This A molecule, we have to apply the sigma H. Now, sigma H is horizontal plane, right? So I've already defined my improper axis as Z axis. So sigma horizontal plane would be along what axis?
Molecular plane only.
Yeah,
molecular-
molecular plane, but what axis? We have to define the coordinates, right?
XY plane. It's
Yeah,
XY plane.
that would be XY plane. So that would become an XY plane. And we have already said that chlorine, 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 and chlorine, they all are at plane. That is like just a paper, right? This particular. Yeah. So if I am applying an XYZ, so this will cut my chlorine into two halves, other chlorine into two halves, platinum into two halves. So everything would be in two halves, right? So it is not going to change my any orientation. It is just like upper half. Okay. So this would be like platinum, Cl2, Cl3, Cl4. Fine. So second operation also we have applied. First is done, C4, and second is also done. Now the third is saying you have to apply a combination of C4 and sigma H. So whenever we have a combination, so here it is saying sigma C4 and sigma H. So whenever we have a multiplication of the operations, we have to start from right to left. We always go from right
to left.
Right?
So first sigma H, then followed by C4.
Right. So already if you start with this complex, that molecule, you have applied the sigma H already. So that we have got this image. We started with A. We got B over here. And now we have to apply what? C4. Along the Z-axis, it has to be perpendicular. What do you expect? What would be the structure?
The same structure which you have written there, the blue color.
Right. So it would be again similar to that of C. So C4 into sigma H, that means S4 is also present in your platinum Cl4. So this way you have to check. Firstly, the operation would be given. You need to see whether the equivalent orientation is coming. If it is coming, that means that axis of symmetry or the plane of symmetry is existing. Second thing is the combination. This is nothing but your S4, right? This
it is
C operation, that improper axis of rotation. So with respect to the S4, you can calculate how many operations of S4 would be there. You have to go from S4 to 4, S4, 4, or S4 to 4, 8 times also until unless identity would come. So I would like to know how many, this would be a homework for everybody. In the next lecture, we can ask that how many operations you will get from the S4. If you apply S4 on a certain molecule, apply it on this particular molecule itself, or do that mathematical way that I have shown for the S3 and find it out how many S4 operations would be there. Whether it would be.
Can we share the slides with us?
Yeah, I would be. Yeah, this slide, firstly, this video would be uploaded on YouTube. As soon as this lecture would be over, maybe you can approach this in the night or in the morning. It would be uploaded on the YouTube, and all these slides would be shared via folder that NPTEL team has already made, so that you will get everything. You will get. Okay, so you can go back and read the lectures and see the slides. And anywhere, if there is any doubt and you have any question, if I can help you with that at any point of time, that would be great. But this time, from next lecture, if you're coming, you are already knowing a lot of concepts. So rest of the people who have not joined, they can go back and read this and watch the videos. And I need to know that how many operations, and you need to solve like properly. If this concept is clear, how to get mathematically from a certain operation, from a certain element, how many operations are going to be there, that job becomes very easy. You can easily, and these questions do come in NetGate and every competitive exams. Okay, so this is way we need to find out. So this is your homework. I will highlight over here. I don't know whether. Okay, so the next question that we have is the S2.
I will rejoin the meeting.
Sorry?
Shall I rejoin the meeting now, or it
will end and you will get to know it automatically. It will end, so you have to rejoin at that time. Until unless we have, I think, some few minutes. Okay, so the S2 operation on a molecule with the axis of rotation on the Z-axis moves the nucleus XYZ to what? So you need to understand each and every word very properly. So what operation it is going telling, that is S2. We know that S2 is improper axis of rotation on a molecule with the axis of rotation Z-axis. That means it is defining, if I'm talking about S2, what would be the axis of rotation corresponding to it? It would be C2.
Yes, C2
Right.
and the sigma perpendicular.
Right. So C2 along the Z-axis, that also they have defined. So from the question itself, you need to understand the language and you need to get your answers clearly. S2 has been given, but on the molecule where the axis of rotation is on the Z-axis. We already know when Sn is there, Cn we are expecting it to be along the same axis, Z-axis. Now it is moving the nucleus XYZ to what? So if I draw this coordinates, that is Z, that is X, and this is Y. So somewhere if it is having X, Y, and Z, that is in a positive quadrant. We have first quadrant, second, third, and fourth, right? Now it is saying when we are applying S2 operation on this one, what would be your coordinates? That is very simple. You do not need to mug up. You do not need to see, even if you don't see your, if you can solve it from this coordinate system, that would be great. If not, then you can solve it mathematically also. So we know that S2 on X, we have to apply on something. Earlier, we were applying on a particular molecular shape, right? Here we have defined the coordinates. X, Y, Z, you have to apply the S2 operation. So that means we have to apply C2 along Z-axis and sigma XY along this XYZ. So you can consider this XYZ as your molecule. So these would be the elements, C2 along Z-axis and sigma, which is perpendicular to your C2. Is it right?
Yes, ma'am.
Okay. Now we have to apply the operation right to left. So first operation that would be applied as
Sigma.
Yeah.
Sigma.
So you can keep this XYZ like this way. We are not applying right now, or we can just remove it. If I will say that I have applied sigma XY on XYZ coordinate. Whenever I am having a coordinate which is on XYZ and I am having a plane which is along the X and Y, which coordinate is going to change? After reflection of
Z.
the plane, only the Z would be changing, because if this is my X and this outward finger is my Y and Z is like this way, if I'm cutting like this, the upper Z would come as a lower Z. That would positive Z would become a negative Z, right? Say for example, this one.
Yes, ma'am.
So this is your plane and it is cutting. The Z is going to reflect it by minus Z. So your coordinates would be
Yes.
X, Y, minus Z. Is it right?
Yes, ma'am.
Right. So now you have to now apply C2 along the Z-axis. So your Z-axis is now fixed. Z-axis is like positive or negative, it doesn't matter. You have to apply the C2 on the Z-axis. C2 is what? How much rotation angle?
180.
Right. So when I'm applying now, this C2 was there and this C2 is along the Z-axis, and whatever the X was in this direction, that would become minus X. And whatever was the Y,
Yes, ma'am.
the direction, that would become as minus Y. So it is going to flip your all the other axes except the Z-axis in your 180-degree rotation. Is it clear? So this
Yes, ma'am.
Z-axis rotation would give your X in this particular coordinate. I should show in this color. That would come as minus X, and this Y as your minus Y. So this would come as minus X, minus Y, minus Z. So this is your answer. So we took a nucleus having XYZ coordinates. It was been said that we have to apply S2 operation. We applied first the molecular plane, which was along the XY axis. The plane was having XY axis. So it is not going to affect X and Y. Only the Z is going to get reflected. We got, instead of Z, we got minus Z because it has got reflected by positive and negative. Now we applied C2 operation, which is a 180-degree, but C2 is along the Z axis. So wherever the operation is going along with, that is not going to change. Despite of that, other operations would be changed. So X becomes minus X, Y becomes minus Y. So if you consider it very carefully,